So the title of my today's presentation is Container Tracking DIY Approach. This DIY means do it yourself. So I will speak about an instrument that my colleague Rade Jankic and myself developed recently for tracking and tracing container in land and sea transportation. And we decided, I will try to justify why, to realize this hardware and software on our own and to see what is happening. So before I start, as you know, my name is Sanja Bauk. I have to mention my colleague, Mr. Rade Jankic, who gave a substantial contribution to the practical realization of this project. This is the way how I conceive the presentation. So I will try to define a problem. Then I will give environmental scan in terms that I will put the whole story into a little bit wider context, in terms that I will give two examples how containers can be tracked and traced in sea and land transportation upon to the solutions which are available so far. And then I will move to the instrument that we developed in terms that I will justify our motivation and introduce you shortly with the hardware and software of the instrument. And also I will share with you some of the preliminary experimental results. And I will end with drawing conclusion remarks and also giving some directions for further research in this field. And at the very end, of course, we will open the floor for questions, answers, and further discussion. So let me try to define the problem. While freight containers are at sea, transportation of data on containers' position and status in close to real time is very limited. Due to the best of my knowledge, only 5.6% of the containers in operation nowadays have telematic devices, which make them, let's say, smart containers or virtually smart containers, so that you can track and trace these containers into close to real time. These are mostly reefer or refrigerated containers that carry temperature-sensitive loads like food and pharmaceuticals. So these containers, small number of them, can be tracked and traced during the whole voyage, including sea leg of the voyage. Having these in mind, we have decided to develop an instrument for tracking and tracing freight container in both land and sea transportation by using so-called do-it-yourself approach. The instrument we developed is based on physical computing, and physical computing involves the creation of a hardware device that can sense and act in the real world. As all of you know, more than 80% of world trade is transported by ships, while over 90% of freight is packed into containers. According to some forecasts under different global economic scenarios, the movements will increase considerably for more than 200% to, according to some predictions, to more than 1000% by 2050. And these are the information that I found in Nature Sustainability Journal. So we can assume that they are close to the reality. Containers tracking and tracing is important for optimal loading and unloading operations, but also for monitoring and controlling the condition of the cargo inside the container, especially when it comes to dangerous, perishable, or temperature-sensitive or goods of high specific value. So in these cases, which are highlighted, it is very important to track and trace each and every container, let's say individually. So in such cases, there is indeed a need to track and trace each container separately, including physical conditions inside it. In road and rail transportation, this is easier to achieve than at sea. Why? There are numerous reasons. Internet at sea is not stable and fast as internet on land due to the sea surface movements, wave occlusion, usual severe weather conditions, the earth curvature, specific multiple feeding conditions at maritime frequency bands, and so on and so forth. Therefore, navigational data and VHF data exchange system services are developed and are used in parallel with the Internet at Sea or in combination with it, aiming to alleviate the above-mentioned impediments connected with Internet accessibility and narrow bandwidth. Containers in land transportation are usually arranged one by one in a single row or in small groups during the trip. Whilst in sea transportation, they are arranged into large blocks, which sometimes count more than 20,000 containers of 20 or 40 feet in length in total. Namely, containers on board ship are placed next to each other in several rows and layers below and above the deck. Therefore, accessibility and acquisition of data become extremely difficult in such conditions. And ship hull itself and its numerous systems can cause a lot of impediments when it comes to propagation of the signals which should follow the containers. Of course, there are always exceptions, and this is an exception. So in this case, we have a dedicated ship for transporting nuclear cargo. And these type of ships have only 20 containers with nuclear waste on board, but still we don't have direct communication between these containers and the control center ashore. As far as I found in the literature which is available, officer on watch is communicating with the control center and sharing information about the status of the containers, because the control center ashore can follow the location of the ship and consequently the location of the containers. But the status of the containers is communicated to the control center via officer on watch indirectly. So there is still no direct communication between these containers and the ship. Since we have time, I decided to put this environmental scan into a little bit wider context and to say something about the regulations of transporting these nuclear cargo in sea transportation, which is really comprehensive. So the main sea trade routes of nuclear material are between Japan, UK, and France, including routes targeting Russia, Sweden, Canada, Argentina, Brazil, Chile, Ireland, South Africa, and so on. And these are the countries which have nuclear plants or have uranium ore. And therefore they are including in this transportation. Some of the countries, for instance, Japan, nuclear waste is exporting to France or to North America. South Africa is exporting uranium to North America because the only nuclear plant in South Africa in Cape Town is not operational because of the poor maintenance, but South Africans are exporting their uranium ore in huge amounts to the North America, which doesn't have a problem with power supply, and South Africa constantly suffered the lack of power supply, so we can make some conclusions accordingly. Legislative framework for coastal states regarding sea transportation of irradiated nuclear fuel like plutonium and radioactive waste correspond to the International Convention for the Safety of Life at Sea, or SOLAS Convention, the International Maritime Dangerous Goods Code, the United Nations Convention of the Law of the Sea, the Irradiated Nuclear Fuel Code, and so on and so forth. Also, IMO Subcommittee of Safety of Navigation Regulation covers the route planning, notification, and consultation with coastal states, including possible restrictions and exclusion of certain routes. Adds equipment and devices that would facilitate location and salvage of ship and or nuclear cargo in the case of emergency are covered by IMO subcommittees on carriage of dangerous goods and radio communications, including both terrestrial and satellite channels, but it's very difficult to find out how this communication works. So I mentioned these PNTL ships, which are specifically constructed and in particular safety built for transportation of this nuclear cargo. And the main control center for this company is in Barrow in France, in England. And so far, they realized more than 200 shipments during the past 40 years, and more than 4,000 of these casks or drums or specially protected containers with nuclear cargo was safely transported from Japan to France and North America. And by the way, company has highly experienced and specially trained crew members. In this slide, you can see how this cask or container with nuclear fuel is loading into the PNTL ship. And it is to be said that these ships are capable of carrying spent fuel, mixed oxide fuel, fuel assemblies, and vitrified high-level nuclear waste. So all these PNTL ships have satellite navigation and weather routing equipment, as well as tracking equipment. These systems enable PNTL ships to follow the safest route and avoid severe weather conditions. The ship's position is monitored at any stage of her voyage. This voyage monitoring system automatically reports the vessel's latitude and longitude, speed, and heading every 2 hours. If the report center does not receive message within a predetermined time, PNTL emergency response system is automatically activated. They have their own planes come on board the ship and provide assistance. But I would like to highlight this sentence. The ship's position is monitored at any stage of the voyage. Ship position, yes, but the status of the container is not automatically observed. So, as I said, the officer on watch has to communicate it. In 2020, I tried to develop a scheme how these systems should function at a very high level of abstraction, as you can see. But my idea was that all these sensors for temperature, for 3-axis digital accelerometer, gamma sensor, neutron sensor, electronic loop seal, rechargeable lithium-ion battery should be attached to this container with radioactive material. And all these sensors should be connected with blink nodes, with wired Ethernet layer network and with wireless sensor network for security purposes. And also we should have digital video system or cameras inside the ship hull with these radioactive material drums to visually control the situation. The most important sensor from my viewpoint is this temperature sensor, especially if we are carrying plutonium as a radioactive waste, because if the temperature of plutonium starts to rise, then it goes exponentially and it can cause a disaster. These sensors should communicate with back-end info communication system with a bridge, and then as far as I realize, officer on watch is using VHF, digital exchange system, specific messages, number 6 for dangerous cargo indication, to communicate in the case of danger with a control center. But there is still no automatic reporting in real time to the control center ashore. And this is something which opens a space for further research. Situation is better in road and rail transportation, and I gave here the example of Argus project, which was developed at Argo National Laboratory in Chicago, in Illinois in USA, in 2008 and 2009. And this project is developed and evolved nowadays to Internet of Things and these widebands. But however, at that time, it was revolutionary because each and every cask with this container cargo should be track and trace remotely in close to real time. And this instrument was mainly based on RFID technology, and it was integrated with GPS and with geographic information system for geofencing purposes. And on the slide, you can see the dispatchers or users interface. So these casks or containers with radioactive cargo can be followed in real time as these green, yellow, or red circles. So if we have green circles, it means everything is fine. If we have these yellow, battery is low, for instance, so it is a kind of alerting situation. And if we have red, it means that something is really happening with the container. Maybe its safety belts are not in place or something like that. And the dispatcher has to react immediately to redeem such a situation. This project was tested firstly with the 14 radioactive material drums at the route from Chicago to Augusta, so from Illinois to South Carolina and the USA, and this was successfully done. And this system works for railway transportation, and it was tested as well. There were just a few several minutes interruption of transmission, but I think with this new concept that this is alleviated and that this system enable tracking and tracing at least these containers with radioactive content in real time with no problem. So let me go to the main topic of our today's meeting. That's these apparatus that we develop on our own. We are aware that extensive research work has been done so far with different methods of tracking and tracing assets at open and closed spaces in general. Today, physical internet is a research topic which concerns goods encapsulated in modular dimension, easy to interlock intelligent containers. The researchers also work on experiments that combine RFID, tag or chipped containers and smart containers on blockchain platform. However, regardless of these advancements in tracking and tracing assets, we wanted to attain our own data through simple practical experiment, which can give us better insight into physical processes in the real environment, firstly in land and later in sea transportation. In the very center of this instrument is a Raspberry Pi computer, and it is connected with the motion or tilt sensor, temperature and humidity sensor, light sensor, and it has power supply through battery and UPS. It is connected with GSM and GPS modem. These modems, of course, communicate with the server, and server communicate with desktop and mobile devices, with laptops and smartphones. These are the components that we initially used, and I have to say that they are relatively cheap. And in the initial stage of the development, the instrument, we put them together on a motherboard in this transparent box. And later, after a series of testing, when we were sure that it works, we put it in this proper box, which can be attached and which is in fact attached later to the inside side of the door of the containers. And you can see the dimensions of this box. It's not so small, but still the dimensions are acceptable. For the purpose of the application programming, we use Python as a high-level general-purpose programming language because it is flexible in terms that it can enhance multiple programming paradigms, including structured, procedural, objective-oriented, and functional programming. In this case, we use Python for the purpose of procedural, reading data and entering these into the database every 55 seconds, and functional programming, setting and triggering the alarms in the case of exceeding boundary values. In fact, Python has been used for communicating the sensors readings to Raspberry Pi database repeatedly, approximately every minute, and also for activating the alarms on the dispatchers or user side in the case that preset sensors values are exceeded from some reason. On the following slide, you will see the pseudocode, its part in fact, that generates functions that will read sensors values of tilt or movement, temperature, humidity, and light, and send these back to the database. The routine for checking boundary values of the sensors is also given. The data were repeatedly recorded into the database in the sequences of about 1 minute, with possible deviations of a few seconds. So here you can see connection with the database, reading sensors values and sending these repeatedly back to the base. The user's interface is a web-based, so this is a, let's say, secure web-based application, and the dispatcher can follow the trajectory of the vehicle on which we load this container and follow it. Firstly, we did it from Subotica to Belgrade, and then from Belgrade to Port of Bar, because our intention was to test it in road and rail transportation, and later I will say a little bit more about that. But the system is functioning. On the following 2 slides, you can see some of the data that we acquire from the sensors. So all these data have a time step, and we were following to these very short time intervals, tilt or motion of the container, temperature, humidity, and light. Tilt was activated in our case only when we upload the container. And we did some intentional movements of the containers, but in fact, during the whole voyage, the status of the tilt should be 0. So the data on the container status, including data recording indicator, values of tire, temperature, humidity, light, and time are captured. During the route, container was intentionally opened several times, which caused light changes until sensor reacted several times because of that, since its boundary level was set at a rather low level. When still exceeded, the limit system gave 1. On another side, it gave 0 if the limit was not exceeded. Time is given as a stamp of about data recorded item. These are readings from a tilt sensor, and as I said, it was activated during the loading operations. These are recordings from the temperature sensor, from humidity sensor. So the next stage in our experiment will be tracking and tracing cargo container in sea transportation. For that purpose, we have to acquire all the documents which are needed, cargo list, custom clearance, waybill, credit letter, etc., and also ethical clearance if we want to send it not only as a freight container, but as a part of research. And some administrative things have to be resolved to allow us to do that. We shall also ask for the permission to place the container on the upper deck so that it can have a line of sight communication to the satellite antenna, which assumes uninterrupted data transmission. Later, we shall repeat the same experiment with the container placed inside the ship's hull without line of sight connection with onboard satellite antenna, and in presence of the obstacles in closed, confined space inside the ship hull. So this research presents a device for tracking and tracing cargo container. It was tested in road transportation so far. The trajectory and the state of motion, tilt, temperature, humidity, and light sensors are captured in close to real time. Raspberry Pi was the key hardware component, while Python was used as a high-level programming language in the backstage. Our plan is to deploy the same device and software in maritime transport, since environmental conditions are different and internet at sea, as I said, is not as stable and fast as ashore so far. I'm coming to the end, because I'm afraid that I was maybe too long. What are the benefits and the challenges of these containers which are equipped with telematic devices, or what are benefits and challenges of these virtually smart containers? Let me start with the benefits. better control and visibility over the supply chain, real-time tracking and monitoring, improved efficiency and decision-making, reduce the number of lost containers, improved cargo safety, reduced risk of theft, reduced unauthorized access to cargo, streamline documentation and compliance with the regulations, and enhance customers' experience. But of course, we have challenges, additional costs. Implementing telematic devices and upgraded containers can increase expenses for logistics companies. Additional resources and expertise for maintenance are required. Data security and privacy concerns are present. Virtually smart containers generate sensitive data, so the measures must be in place to protect against unauthorized access and data breaches. And also compatibility and standardization is always an issue. And also national legislation might be different for different countries in this world that has a tendency to be global one. So all these are challenges, but still there is a lot of benefits, and it is worth to go further with these experiments. I would like to thank you for your attention and to apologize if some segments of my presentation were maybe too long or a little bit boring, but we can correct this to the following discussion. And also before the end, give me opportunity to announce the upcoming event on 18 October this year. At the same time, from 3 to 5 p.m., you will have opportunity to listen this gentleman, Bratkov, who will give the talk on the new ferry concepts to be developed by the Finnish Delta Marine Ltd company. So this is also an invitation for the upcoming event before we move on with your questions and comments and whatever. I really would like us to open the discussion here in the room and also online. Thank you very much for your attention.
About commissions.
Yes, please.
Okay, firstly, thank you for your presentation. This is presentation. It's not boring, believe me. Question is, can you go back to slide with the drums in yellow and so on?
For a sea transportation or for
your nice picture with the proposal.
Sorry, I have to go back to my presentation mode. Yeah, okay. This one. Okay.
This, not this one. I think next one.
This one.
Where is slide with yellow and red? Rounds.
This one.
Oh, this one, yes. But okay, yellow this indicates what battery is low, for example, yes?
Low battery, yes.
Low battery. But what about red? What is it? It is overheating or leaking or something?
It's a mechanical problem on security of the drum. The safety belt on around the drum. People can't hear me. I need. Because of the audience in MS Teams, I need a microphone. It's a technical problem with the drum itself. It has some kind of safety shock belts. And if you have a movement of the container, then that belt can be unfastened. And as I found out by reading this paper, it was a case that we have a movement of the container and that safety belt was not because of that properly fastened. And it's a rent indication. You have some kind of shock on the container, and that shock is represented like a red.
But okay, it's easy to take measures on the road. Stop this vehicle and so on. But what about sea? It's impossible to take some measures.
Yeah, it's in these containers, as far as I realize, on the ship are extremely well fastened. You know, they have something like beds in which they place them on these ships with nuclear cargo. They have something like a bed, and on that bed, it's fastened container, so that they protect the inside, the load of the container to be moved. These containers are with a double protection, with so many protections, so that the waste inside is somehow blocked, fixed, and that the movement is enabled.
I imagine the problem will be with autonomous systems. No people on board.
And I was reading about this. It was very interesting to me.
We will have information, but we nothing can do.
Yeah, fortunately. Yeah, and also in the case of need, they have some trials in real scenarios. So the plane come on board the ship and specialists are doing interventions and all that. And this is a very, very safe system, checked so many times, and luckily with a zero accident so far. So no accident is recorded because the disaster should be terrible. Thank you so much. Thank you so much. Do we have okay?
Yes. So can you hear me well, or is everything audible?
Yes.
Okay.
We can see and hear you. I can see you, but I'm not sure that audience here can see you. Yeah, it's a little bit tricky.
Okay.
But anyway.
But anyway, maybe I can just ask this question that I have. So as I understood, this system is about like collecting numerical data primarily, and then checking if certain values are falling within expected ranges. And this question now I have is now motivated by the fact that actually you might not always have enough like network connectivity with the central location where monitoring is conducted. And question now is actually what is the processing scheme of those numerical values which are collected? So let's just assume that you are querying for temperature. And you already also know that there is a certain range into which this temperature must fall. And maybe it is between 20 degrees and 30 degrees, just to provide as an example. And if now those thresholds are violated, so it doesn't matter whether the temperature is higher or maybe lower, then this is maybe regarded as some sort of fault condition to which one has to react. So this is just a simple scenario. But my question now is where actually is this? Are those thresholds now checked? So does it happen so that these thresholds are already checked inside the sensor itself, which is inside the container? Or is actually these thresholds now evaluated on this central monitoring location? So where does it happen? Is it local, or is it happening in a central location?
It is happening in a central location.
Okay.
Sensors are just scanning the real situation, and the boundary values are set on the server side.
Okay. And then actually one proposition I actually what I could just suggest is that one direction for like maybe which might be worthwhile to evaluate is actually move this calculation which is done to the sensor side. And why I'm now suggesting this? So there are actually several reasons. So one of them is load distribution from a central location to the sensor side. And it might look like it's not maybe so important question, but actually when you are monitoring really a large number of sensors, let's just say that you roll out this system in production and the number of use cases will just grow really fast and the solution becomes really popular. You might have like tens of thousands of such devices, around, and then sending, queries over the network to these devices. This will actually consume a lot of network bandwidth. And even the load of this central server might actually increase. So one sensor is nothing, and maybe even 100 sensors. This imposes really a small load. But in the end, when you move up to a really large scale, you have sensors distributed all over the globe, and their number maybe even grows to hundreds of thousands. Then this is already a significant load. Even the processing load in the local server it's actually becomes quite heavy, and the network communications as well. And when you move this computation just to the sensor side, this actually offers a really nice way of reducing this load significantly. And then also you don't even need actually to execute those queries or transmit this data over the network at all. So all the queries are just locally done. And then all you have to now communicate over the network is just an alarm. It's just one-time alarm. And this will drastically reduce the amount of network bandwidth you have to consume. Also, when the connectivity is really limited with vessel, then again you save quite some bandwidth. And also this central server or central location, this becomes much less loaded. And this strategy quite often is even utilized in monitoring systems, which are really large scale systems, like in telecom networks. If you need to monitor a huge number of devices, then it is quite often what gets done in such environments is that you move this computation from central location to the sensor side. You distribute essentially this workload. And also actually this threshold checking is not so expensive operation. So the sensor, I imagine, can just handle it locally. And this is actually one direction I would just suggest, but this is just a suggestion.
Thank you so much, Risto. A very valuable one and very thought-provoking. But I have to say that we use the components from from the basement, very cheap one, and didn't think about that maybe we should employ smarter sensors. And also we have a problem how to set these values at the beginning, and we do it in a way that we just scan the temperature and that our light sensor reacted only when the door are open, something very simple, Mm-hmm. And also this tilt sensor is very tricky when it comes to containers, especially if they are on board the ship. Usually that tilt is big, and it's not possible to prevent containers to fall into the sea, for instance. So that's another issue in sea transportation. But we just started from scratch and would like to see how it works, and we were all happy when it was working, but it doesn't mean that it will work smoothly at sea at all. Especially we plan to send it on a destination from Port of Bar to Port of Bari, and we know that the satellite connection is very pure on that, sea area. We are aware of that, and maybe the system will not work at all, but we just would like to check it. And after that preliminary check, we will go further. And I would like to thank you very much for this idea to to move the activation of the sensor from the side of the server to every single a sensor, and to reduce the network traffic. Thank you so much for your suggestion. Thank you. And I somehow have to check, do we have more questions in MS Teams? But I can't see any hands here. Maybe we have something in the chat. Okay.
question. As satellite internet coverage expands, somebody like Starlink, online, how do you see this situation changing your research?
It's a good question, but I still think that the biggest challenge and the biggest problem is the number and the arrangements of these containers on board the ship. And the capacity of computers for processing these data are limited. And the other issue is that, how to say, transfer of the signals or propagation at sea. So there are two or more layers of the problem in this particular case. And don't forget, we are just doing experiment with one container. But what does it mean in terms of following a huge amount of containers on board the ship? But at least I mentioned this example of transporting nuclear cargo when you have only 20 casks on board the ship. And in that case, we should discuss that option. And yeah, I do believe that in the future, that problem of stability and bandwidth of internet at sea will be resolved. But when, I can't say at the moment. But I do believe it will be resolved as well. It has to be, in terms not only on transporting containerized cargo, but also in terms, as Anatoly mentioned, of these autonomous vehicles. And we were discussing before the meeting, we have sea surface unmanned vessels, we have underwater, and we have aerial, and sometimes they have to communicate. And these are the real problems and challenges in front of the researchers in this area. I'm not sure, did I answer your question, but I just tried at least. Yeah. Let me see. Do we have any more questions from the audience here in the room? No? Okay. I suppose that you might be tired. I would like to thank you for your attention and also for participating into this discussion afterwards. And yeah, to wish you the pleasant rest of the day. Thank you so much. Thank you.